The equation of continuity. Ideal flows in motion. Here are 4 assumptions that we make about our ideal flow. What is ideal fluid? 1. Steady flow. In steady flow, the velocity of the moving fluid at any fixed point does not change with time, either in magnitude or in direction. 2. Incompressible flow. That is, its density is a constant, uniform value. 3. Non-viscous flow. An object moving through a non-viscous flow would experience no viscous drag force, that is, no resistant force due to viscosity. 4. Irrotational flow. In irrotational flow, the test body will not rotate about an axis through its own center of mass. So many secrets like this: smoke cigarettes, okay, the car, intestine, and so on. A fluid element P traces out a streamline as it moves. This is a streamline. This is a flow elements. Okay. The velocity of the elements is tangent to the streamline at any point. A streamline is the path traced out by a tiny fluid element, which we may call a fluid particle. As the fluid particle moves, its velocity may change both in magnitude and in direction. However, its velocity vector at any point is always tangent to the streamline at that point. The streamlines never cross, because if they did, a fluid particle arrived at the intersection would have 2 velocities simultaneously, an impossibility. A tube of flow is the tube whose boundary is made up of straight lines. Assuming that the fluid is incompressible and cannot be created or destroyed, thus, in the same time interval, the volume of flow which comes in the tube must be equal to the volume of flow which goes out of the tube. 3 conditions. Okay, 3 conditions. Okay. This is the fluid is incompressible. Second, it's not created or destroyed. The equation of continuity. Look at this tube, a streamline tube. Okay, we see this one, the value tube is going in, and at the same value, the green one is going out. We see, okay, the fluid flows from the left to the right at a standing rate through the tube segment of length L. Okay, what is this? This volume is the area AI times VI. XI is VI over T. Okay, and this out in are the same. So we have AI VI delta T equal to delta V in equal to A to V2 delta T. We cancel delta T, we find out AV is a constant. This is called equation of continuity. Sample. The cross-section area A0 of the aorta, the major blood vessel emerging from the heart of a normal resting person, is 3 centimeters square, and the speed V0 of the blood is 30 centimeters per second. A typical capillary diameter 6 millimeter has a cross-section area A equal to 3 times 10 to the minus 7 centimeters square, and a flow speed V of 0.05 centimeters per square. How many capillaries does such a person have? We know the continuity flow. Okay, So A0 V0 equal to NAV. This is a capillary. Okay, this is aorta. Okay, and we put the number inside, we get an N. Very simple. 6 billion, very huge in our body. Figure shows how the stream of water emerging from the faucet next down as a fall. The cross-section area A0 is 1.0 centimeter square, and A is 0.35 centimeter square. The two levels are separated by vertical distance h, 45 millimeter. At what rate does the water flow from the tap? You want to find the AV actually, okay? Now, let's see this one. We see AOVO equal to AV. This is a continuity of fluid, okay? And what the relationship between VO and the V? Because it is a free fall acceleration. So we have V squared equal to V0 plus 2GH, okay? So we get this one, and we put this one. V is AV0 over A equal to V0 plus AV. In this case, okay, in this case, we know A0, we know A, we know H, we can find the V0, okay? Let's get the V0, okay? Once we get V0, we can get this one. The A0 V0, okay? 1 second, you have 34 cubic centimeter.
This water-filled cylinder is attached to a motor so that we can spin it at a high speed. When the cylinder is spinning, what will happen to the surface of the water? We'll begin by spinning the cylinder slowly, then increasing the speed. At first, the water surface stays more or less horizontal. As the speed increases, the water begins to climb up the wall.
This is covered parabolic.
When the speed is great enough, the parabolic shape of the water surface becomes clear.